here. A few weeks ago, I was on campus, and it's a beautiful, beautiful campus that they have there in Shiliguri. Right? But it's a nice morning, and unfortunately, I'm a little bit under the weather, so you might have to all deal with a very nasal voice today. That aside. Enjoy the talk. I wanted to be engaging. I wanted to raise questions because all of you are faculty members here. All of you are running various student projects, various research projects across the country, right? And I want you to take away from this talk about the complexities that we deal with in an IoT-based solution, especially when it comes to taking a solution from a lab to the market, right? Of course, a lot of the solutions depend on the complexities that we kind of see during implementation, right? So today I'm going to focus on one particular aspect of an IoT solution. I'm going to look at smart lights, smart street lights as an example, and see how we can develop intelligence in something as mundane as a street light, and develop the level of complexity and the kind of solutions that we can build on top of it, right? So look at it in the context of a larger ecosystem. Look at it in the context of all the digital transformation that is happening in the country, in conjunction with, say, the biometric database that we have in terms of Aadhaar. Look at it in conjunction with the payment integration mechanisms that we have under UPI, right? Look at it as in the context of our GSTIN network, right? The e-governance projects. All of these kind of tie in together. And for those of you who are actively looking for projects to incorporate IoT in, I would strongly recommend that you look into a website called API-SETU, right? API-SETU is the Government of India portal, and it basically publishes all the active APIs that are used in various government websites, right? This includes your, vaccination, your vaccination reports, your Aadhaar integrations, your insurance integrations. So there's a lot of opportunity to create new applications in that space. Right. With that introduction, I'd say that we have a very little time today, so I'll get started on the talk itself in terms of why should you care about IoT. If you have questions, you can look me up on WhatsApp. You can ping me there. I'll not be able to see the question screens coming in, but we can take questions over there as well. Right. Three major things that I will talk about. Why should you care about IoT? What does the IoT technology stack look like? And the third thing is really about how the street light improved its IQ and became smart, right? As an example of a smart application. I'll start with a little video. Perhaps it will wake you up a little bit.
Every morning at 4:30, you hear the cooks talk on the floor. It's hard times in the mill, my love. Hard times in the mill. Every morning just at 5, gotta get up, dead or alive. It's hard times in the mill, my love. Hard times in the mill. Every morning right at 6, don't that old bell make you sick? Hard times in the mill, my love, hard times in the mill.
Right. That audio may not have been very audible to many of you, but the core message that was being passed along in that ad was, as family men and women, we know that things can get tiring. right? And in this particular ad, the lady is tired from looking after her family, and she kind of dozes off on the road. The car can figure out that there is oncoming traffic and steers her to a path of safety, right? To a large extent, that is what IoT is for me, right? IoT is invisible, right? Because it has started embedding itself in our surroundings, right? And these are real life applications where IoT is making a difference to life and death, right? That's where IoT is. And although we kind of tend to think of IoT as a modern marvel, as something that has evolved in the last few years, it is actually not so, right? Because the first mentions of such a system, if you look at one of the earliest papers that was written by Mark Weiser, former CTO of Xerox PAR. This was a paper that came out in Scientific American in 1991, right, where he really talks about the computer for the 21st century as specialized elements of hardware and software connected by wires, radio waves, and infrared, which will be so ubiquitous that no one will notice their presence, right? So the concept of having computation all around us, having computation and communication embedded all around us, so that they operate seamlessly with us, right? Help us in our day-to-day activities, oversee the kind of activities that we do, prevent failures, improve productivity, right? The vision for that was already there 30, 40 years ago, right? Remember, this was the time, late 1990s, late 1980s was a time when probably the personal computer had started to come into the market, right? It was a big shift from having to queue up for time on a mainframe computer and instead have a dedicated computer at your home, right? That was a big deal. Thinking about embedding computation all around us was a leap of faith, right? It wasn't really science fiction. So even though we saw Weiser, he had been talking about it from 89 onwards, but even though Weiser kind of came up with this paper on ubiquitous computing, or pervasive computing as it was kind of known, right? In 91, he had been talking about it, and people generally wanted to connect things to the internet from very, very long ago. In fact, the first IoT device, right, the internet toaster, came out in 1989. It was demonstrated in 1989, 2 years before the first web page came out. Just think about that. Before HTTP came out, before URLs and hyperlinks came out, you had an internet-connected toaster that was working over TCP. It was using SNMP frames over TCP to connect to trigger relays, right? So the desire to create internet-connected devices has always been there. It is just now that it's become a lot more simpler. It's become a lot more simpler because we are bringing in, we are seeing the effects of, Moore's law, right? The reduction in computation cost, the reduction in power cost of computation, the increase in bandwidth, the ability to achieve higher physical ranges with wireless communication, right? And being able to control that kind of radio structures, right? Being able to do multiple concurrent connections, right? Those are the fundamental attributes on which IoT is built today. And we see IoT today as a bunch of these smart applications, right? We kind of tend to associate IoT with these smart applications. We call them smart buildings, smart vehicles, smart farming, smart cities, smart healthcare, smart home. Everything is smart, but we have not defined what the smart in this smart application is, right? Without that definition, what ends up happening, and I see that in a lot of my discussions with faculty members, is it ends up, IoT is a game of a few blind men and an elephant, right? what exactly is IoT? Is it just embedded systems plus plus? Is it just the design of creating low power devices? Is it about the architecture of a particular deployment strategy? Is it about a mobile app that connects to sensors that are found in a mobile phone today? Is it about being able to bring a device that I purchased in a foreign country and making it operate in our country, right? Is it about regulations? Is it about interoperability and standards, right? Is it about automation? Is it about convenience? Is it about low power radio, right? So there are, we tend to look at IoT from where our backgrounds are. And that's not necessarily a bad thing. That's not at all a bad thing, because when we bring in our backgrounds, we bring in our areas of deep expertise and use that to probe a new aspect of IoT, right? IoT is all of that. IoT is all of that because unlike a regular system, unlike the kind of systems that we are used to, which are more homogeneous in nature, which have a very consistent protocol stack, which clarity that is built into it, IoT systems are more distributed, right? IoT systems are, the IoT technology stack is a little different from what we are traditionally used to thinking of when we think of stacks, right? What does this stack really look like? So if we were to deconstruct one of these smart applications, whichever they might be, right? Whether it's a smart city application or a smart home application, right? Fundamentally, there are four major aspects to an IoT application, right? The first aspect, of course, is acquiring the data. Devices, right? You have devices out in the field which are, right? They could be, there could be multiple devices in the, right? For example, in a smart home application, you could have internet connected, light. You could have internet connected window blind, right? You could have an internet connected TV, right? So these are things which are in proximity in a smart home, right? Or you could have systems that are more spread out, like in a smart city, right, where you have various kinds of sensors all around you. Right? So fundamentally, it's about getting data from whether these are sensors which are on your body, which forms a personal area network, or in your home, which forms a slightly larger home area network, or even slightly larger, which is a site area network, or something that is collecting data from a building, or something even larger, which covers a metropolitan area, or a metropolitan area network, or something even wider, maybe a wide area network, to something that is probably regional, right, which is like an earthquake detection system, or a hydrological system, right, which may cover even larger areas, right, which is a wide area network, right? So the scope of where this data is coming from could vary, and that's where the communication infrastructure comes in, right? So it's about getting data from heterogeneous devices, each of which are have diversity in their in their sensing capabilities, in their computational capabilities, in their communication capabilities, in their storage capabilities, and in terms of their power availability, right? So the first step really is acquiring the data from this sensor network, right? This plethora of sensors that are all around. Creating a backbone to bring all this data together, right? Using a communication infrastructure. Whether that communication infrastructure is operated by a third party, like in the case of narrowband IoT, or in the case of LoRa, right, or Sigfox, right, or it is operated by the provider of the solution, right, like a Zigbee-based solution or a Wi-Fi-based network, right. So there are about 100, 120 odd protocols that are available for communicating from a particular device, bringing the data out there. Now you also have to understand that over time, this kind of automation has been happening in various areas, right? Because it has been happening in various application areas, several protocols had been created over time. Right. So if you are looking at a smart home or a smart building solution, you already have protocols like KNX, like DALI, which are being used for lighting networks. Right. If you're looking at a smart vehicle, right, you already have a CAN bus protocol, right, car area network. Or protocols like OBD, onboard diagnostics, right? So each industry had kind of developed their own set of protocols to work with the devices that they are most familiar with, right? Home automation, some of the biggest players there had been typically Zigbee and Z-Wave, right, on the protocol side. Nowadays, we see that getting replaced a lot with Bluetooth and Wi-Fi based systems, right? Because we have these two protocols available on our cell phones as well, right? So the first part is acquiring the data, right, from that entire network. The second part, of course, is once you have acquired the data, what do? You process the data, right? How do you process the data, right? One of the key things is there is a fundamental shift in the way you think about IoT-based systems, because unlike the traditional internet, right? In the traditional internet, there is a client-server architecture, which means that the server serves, the client consumes. In the internet, the server is available at a well-known location, right? Typically, it is an address, right? You could go to a domain name, www, say for example, www.ndtv.com. And you have domain name servers, which will resolve it to a particular IP, and you can send an HTTP request to that particular IP, right? With IoT-based systems, there is a fundamental challenge over here with this kind of a network. Why? Because you see, when you are doing an HTTP request, you are opening up a TCP channel with the network, right? If you're opening up a TCP channel, it means that you are keeping that channel open because you expect further communications to happen, right? And the moment you are keeping that TCP connection open, if you are on a battery powered device, that's bad news because your radio is turned on, right? It's a longer, and radio is one of the most expensive components, one of the most, it's one of the energy hogs on your system, right? So TCP, bad news for IoT devices, right? So IoT devices are going to shut down their radio every now and then because we want them to consume their power as much as possible, right? The second thing is that it is very, very likely that the IoT devices are sitting behind a gate, behind a firewall. You don't want these IoT devices to be up there in the public internet, right? So their IP addresses are essentially masked by this site gateway, right? So this is like a local network behind the site gateway, right? Now you see the problem now, right? The problem is that the address of the server is no longer available, right? So it cannot use the typical client-server architecture that you would normally use in a IoT-based system, right? You need something else. That's where new kinds of application layer protocols are being developed for IoT systems, right? This includes protocols like, modifications to HTTP called HTTP long polling. It includes protocols like WebSockets, right? It includes telemetry protocols like MQTT. It includes next generation low power protocols like CoAP, constrained application protocols. These are protocols that you are using to establish more of a publish-subscribe model between the site gateways, between the devices and the cloud infrastructure or your so-called server infrastructure, right? And this kind of this kind of architecture you get into because you want to preserve the lifetime of the network, right? But once the data is there, right, you are building your application, right? You are building your application, and it's like any other IT application that you build, right? You look at the kind of data that you are bringing in. Is it time series data, or is it event driven data that you are looking at? And you have multiple database options that are available to you depending on the type of data that you are handling, right? You have systems like you can go with a regular SQL, but SQL does not really scale very well, right? So if you're handling a lot of data, SQL is going to be a problem, but it's going to give you very fast response times. Or if you're not sure about the kind of data that's going to come in, you can use a document DB, right, like a Mongo. Or you can use a time series database like a Cassandra, right? Or you might be more interested in splitting the incoming data into multiple streams and running algorithms or filters on them in parallel, right? And that is where a system like Kafka might come in, right? So there are multiple choices for building your application backend, right? You might want to run some machine learning algorithm on them, right? So it's not necessary that you have to build all your machine learning models, right? If you are working with any of the major cloud providers, right, be it an Amazon, be it Google Cloud, be it an Azure, be it IBM system, right? You will find that there are a number of pre-canned machine learning services that are available to you, right? Whether it is for natural language processing, whether it is for OCR, whether it is for time series regression models, right? These things are already available to you, right? So when you are building an application fast, you want to integrate as many of these third-party services as possible, right? Because if you're building a scalable system quickly, you don't want to get into building your own user management system, you building your own authentication mechanisms, right? We use as much of third-party systems as possible, right? Because these are tested, scalable systems, right? Once you have established the scale, once you have established the application, then you go back and try to optimize on the cost and the deployment methodology, right? The third aspect after you process the data is that the data must be useful in some form, right? It must be able to develop some insights, right? So just pumping the data out as it was does not really make a lot of sense. So you prepare the data for human interactions, right? Whether it is in the form of actionable items or notifications that you send out on a mobile app, right? Whether it is a chart or a graph or a dashboard that you build on top of that you build as a web app, right? Or whether it is a report, a PDF that is created and sent out for posterity or printed out for posterity. All of these are essentially forms of the data that you create to bring in a human in the loop, right? Which may or may not be required. In certain cases, the decision can be autonomous. And in that case, whether you have that autonomy or not, whether you bring in the human interaction, the idea there again is to close the loop, right? Is to send back a control signal in order to close the loop. Now, different applications have different latency requirements for closing the loops, right? If it is an industrial machine, then the latency requirement is very, very rigid, is very tight, right? If it is a convenience application, right? For example, it is about giving you, switching on a smart light the moment you press the button, right? Even if the delay is of the order of a second or so, it is within, human. It is below the threshold of human perception, so it doesn't really matter, right? But if it is a machine that is processing hundreds of or thousands of readings per second, then that latency has to come down in the sub-millisecond level, right? So the bounds of your infrastructure, right? The complexity of IoT applications really comes from the vertical, the application use case that you are dealing with, and the specific challenges of that particular area, right? Also, if you figured out that IoT applications, it kind of needs a new workforce. It needs a workforce that kind of thinks a little bit more laterally, right? Of course, with IoT, you have, you have the regular jobs, right? You still need your mobile app developers, your front-end developers, your back-end developers. All the traditional IT roles are there, right? Your UI designers, your business analysts. But along with that, right, you now have a plethora of new roles, right? You have the control room operators, you have the ML developers, the semiconductor industry chipping in, right? Low power device engineers, your PCB designers. Everybody has a role to play in building these IoT applications, and therefore, in my view, right, the IoT technology stack is not vertical, it is in fact horizontal, right? It is horizontal because you need to have embedded devices that are created using microcontrollers, low power radios, sensor integration, right? There's a lot of development that is going on there. And typically you work with C-based APIs, you work with specialized IoT protocols like ROLL, like UDP, Tiny DTLS, CoAP, lightweight M2M, IPSO, right? These are the kind of technology stacks, networking stacks that you deal with on an IoT embedded system on the smart sensor, right? The gateways are relatively more heavy-duty devices. They have significantly more computational and storage capability than the IoT devices. So they kind of act as local or site aggregators. You have the same C-based APIs to listen to the field network, but at the same time, you now have some of the IP networks, right? You have the TCPs, you have the SSLs, you have the HTTP stacks also starting to run on the gateways, because they are bridging the resource gaps, right? The computational disparity between the field device and the cloud-based devices, right? The cloud-based devices are, again, which are all more Linux-based systems, Linux, or they're running LAMP stacks, or they're running WAMP stacks, right? So they are talking full HTTP, they're full on, they understand REST protocols, right? They could be clustered, they could be running in one machine, or they could be clustered across several machines running within a virtual private cloud, right? Or this could be something that is running in your IT infrastructure as well, right? Giving rise to a bunch of these RESTful APIs or HTTP APIs, if you're more familiar with them, and that can be integrated with mobile apps, right, which are built using Android Studio or iOS Studio, consuming these APIs for data refreshing, right? Or you could be working directly with the sensors in the mobile app itself, in which case the app kind of becomes a device in this network as well, right? In other cases, you could use this as a backend and integrate front end onto it. So you have different kinds of applications that you build, right? And these applications really are built based on the domain that you are working in, right? For example, I classify these applications into 4 major categories, right? For example, if I categorize them as consumer electronics, then typically for consumer electronics, I expect somebody to have 1, 2, 5, 10 devices associated. So the objective of consumer grade applications is really convenience, design, comfort, right? These are the main attributes when you come across consumer grade applications, right? Usability becomes the key word, right? Whereas if you're looking at enterprise IoT, right, this is where applications are being built to keep track of productivity, right? Whether it is attendance monitoring systems, or it is biometric identification and and things like that. The objective is to create more of an enterprise application with lots of information, maybe hundreds of nodes in deployment, right? Control rooms in place so that you can generate reports about productivity. The third category is the industrial IoT systems, where the focus is on operational efficiency. And operational efficiency comes from either being able to minimize unplanned outage in the network, right? Or being able to improve the usable components per unit of input components, right? So both of them contribute towards operational efficiency. And typically with industrial IoT systems, you will find much more high-speed, high-velocity networks. You will find a core information gathering network connecting the devices, and insights being generated and shared across corporate boardrooms where the top-level productivity is getting monitored, right? But again, the focus is on optimization of resources. With smart cities, the focus is different. The focus is for citizens. It is a government initiative. Typically, deployments are of the order of thousands, tens of thousands of devices, right? Therefore, there are control rooms that are created to monitor the usability of the system, right? Typically, there are it's like think of it like a metro rail, right? The government kind of spends the money upfront so that there is a benefit for the citizens that is available over the longer duration, right? So while you can have something like a smart light application, right? In the consumer world, a smart light means being able to turn on your light from a mobile app, right? Whereas in enterprise IoT, it may mean that you turn on the light based on human occupancy of a particular seat. In Industry 4.0, lights may involve specific lights that are used for a particular production, right? A specific using a specific task lighting with a particular wavelength so that it improves productivity, right? With smart cities, smart lights could be about managing large networks of street lights, right? So it's the same smart lighting application, but with the change in domain, with the change in the audience of the system, your application constraints kind of change a little bit, right? So today I'm going to probably go a little bit deeper into the smart city example, right? Look at what are the multiple applications. Like a smart city itself is not one thing. It's a plethora of different applications and different vendors providing the same application in different wards or in different municipalities, right? Just like when we create parking zones in a city, it's tendered off to different service providers or to different contractors in different parts of the city, right? So you cannot expect the same solution to be provided by the same vendor across the city, because we don't want a monopoly over there, right? And IoT in smart cities, it involves multiple applications. It could be for finding out, making reservations about a parking spot, right? Remote control of traffic lights, or disbursement of ambulances, right? Or collecting waste, or detecting that waste has to be collected, right? Public transportation, letting the citizens of the city know when a public transport will be available, so that they don't waste their time standing at a bus stop, right? It improves productivity for all the citizens, and therefore it kind of frees up time for people, and that free time contributes to economic activity. That free time contributes to, even if you say that somebody who does not want to saves 30 minutes by not standing at a bus stop before the bus was due, even if the person goes home and spends 30 minutes watching TV, remember that there is, watching TV is an economic activity, because a TV production is being made for that person to go and watch TV, right? Production is being made because there are advertisers who are funding that, right? So even if it is doing nothing, it is still contributing to economic activity in some way or the other. I'll go in one more level and look at street lights, right? Specifically, what can I do to make street lights smart, right? Uh, Let me start off with saying, everybody has seen a street light, right? I don't think I need to introduce what a street light does. But from the halogen lamps, right, we have moved into a lot of LED lights, and LEDs are extremely effective, right? They are effective, but fundamentally the change that an LED light brings in is not only does it produce more luminous, and you can see from the luminescence isolines that they have greater coverage in between two poles, but fundamentally I have made this an electronic device, right? Instead of running on 220 volt, I am now running, I have power conversion circuitry inside the luminaire, right? I am now bringing in power conditioning circuitry, converting it to DC voltage, and I am bringing in digital electronics inside the luminaire, right? But how does it switch on? Well, somebody walks around and in the evening and switches it on, right? So it's not the most effective way of, I mean, if a human is going around and switching on all the lights in a particular area, clearly there is no IQ to my smart light, right? So let's look at what can we do to improve that, right? Here is my caricature of the street lamp, right? The first thing let's do is let us know where these street lights are, right? So if I build an IT application and every time I'm installing a street lamp, I geotag it on a field force application, right? Or every time it has to be installed, a street lamp is being installed, just go near the street lamp and mark its location, right? By just doing this part, essentially using the app as a GPS sensor, I'm now able to create an IT application which shows where my street lamps are distributed across my city, right? I can use this for offline reporting of faults. So if a customer calls me from their home and tells me where their home is, I can take a report noting down which light is not working, right? Also, I can use this to kind of have a count of how many lights are there, how many, when was the maintenance schedule last performed on which light, right? So I can have some metrics coming out of just this IT application itself, and therefore I have given it a little bit of smartness because a lot of information is now available at my fingertips now. Right? What else can we do? Well, the next step up would be to see if I can put a little radio on my street lamp, right? And I can at least open up a one-way communication with my street lamp, right? At least if I can send it an on, off, or dim commands, right? My application, because I'm now communicating directly with the street lamp, I'm going to call this an IoT application now, right? Because I have devices that are talking to me. With this, what can I do? I can do remote operations. So I can click a button and a light will come on or off. Or I can put this into an algorithm, into a schedule. And I can say that, at 7 o'clock, start off at 100% because people will be gathering around. And then as you get to around 9 o'clock, 10 o'clock, there'll be fewer people around. You can reduce the brightness level. And then you're getting into the dawn time when you do not need as much lighting. And you can have the lights turned off from sunrise to sunset, right? So I can set a schedule, right? I can not only set a schedule, I can create a schedule that is based on my calendar, right? I can create a seasonal schedules, right? Additionally, I can start hooking up with existing weather APIs, right? Weather stations as a service, and now I can have weather-based. I can have dynamic weather-based schedules, right? So schedules can be predefined or they can be weather-based, right? Because what else does this allow me to do, right? Now I know, or rather, the system knows when a command to switch on a light was sent out, right? And when the command to switch off the light was sent out, right? So accordingly, I can make estimates about my energy consumption, right? So this kind of gives me a ballpark sense of how long my lights are expected to last. Right? What else can I do? Right? Well, what if I add on a little bit more complexity to my light and say that instead of just being able to send one-way communication, what if it's bi-directional communication, right? And I can collect the usage data. Right? Because the usage data does not take a whole lot. I put a current ring around my around the wires, around my inputs, and I will get a sense of how much current is being drawn by the system, right? So now, with just this little addition, I don't need to estimate the energy usage. I can now calculate the energy usage, right? Not only that, if I can calculate the energy monitoring, what I can do is I can now start to create a vendor product scorecard. Right? What that really means is I now know which vendor's bulb I put in each of those luminaires. So by calculating the usage, the runtime of the bulbs, I know exactly what their mean time to failure is, what is the stated mean time to failure versus what is the actual mean time to failure. And that will help me as a city understand whether the lowest cost vendor is really the optimal vendor for the city or not, right? It helps me save money by identifying unscrupulous vendors who are lying about their products, right? It helps me do pilferage detection, right? Because I know exactly how much power it is expected to consume as per the product data sheet of the light, right? If there is additional consumption, if there is sustained additional consumption, or if there are peaks of consumption, then I know that there is pilferage, right? And pilferage is bad because the city is paying for it. The city is paying you, me, all the taxpayers are paying for electricity that they are not able to use for economic activity, right? So pilferage detection, that is something that can be done, and you know exact energy light consumption, or rather the consumption for use for the lighting purpose, right? What else can we do, right? So I think we will all agree that so far I've gone up on my IQ meter and I am adding on complexity, right? I'm adding on more things that we can do, right? Now, what if I add, not only the ability to collect information about energy consumption, what if I add a little bit of a sensor which collects my ambient conditions as well, right? What can I get out of that? Well, if I do light levels, right? If I do light levels, ambient light levels, then I can do ambient light-based automation. Why is that useful? Well, my street light could be located in a place where I have a bunch of other shops which are switching on their lights. I have a bunch of other houses which have their gate lights on. So I really do not need to reinforce that lighting with additional light because it does not serve any additional purpose, right? So I can use ambient lighting conditions to figure out if some lights should not be glowing at their full capacity. Now remember, we are using LEDs, right? Unlike halogen bulbs, which have to be either on or off, unlike resistive lighting technologies, which is again heat-based, with LEDs, the power output can be controlled using pulse width modulation, right? So I know exactly how large my pulse should be to know how much I should be what should be my lighting output. So I can control the dimness of the light effectively. So with lighting levels, I can get ambient lighting. I can get ambient light-based automation. What if I get sound levels, right? If I get sound and noise levels, it now allows me to start building these urban pollution models, right? Which could be about carbon dioxide trapping, which could be about sulfur dioxide trapping, which could be about sound trapping that is happening, right? It could allow us to identify regions which are subject to higher noise and then pass on that information to civic planning bodies, right? So that so that it can be corrected, right? Sound barriers can be put up, or further construction is limited, right? So now what we are starting to see is departments starting to come together in a more sustainable form based on actual live data, right? That's how we start using technology for integrating departments, for building synergies between the users, the residents, and the government, right? The government and the businesses, right? That's the synergy we are trying to unlock, right? That's where IoT comes into the picture. Moving on, what else can we do, right? If you monitor temperature and humidity, it allows us to find heat maps and heat traps within a city, right? It tells us if there are glass buildings facing each other, then light is just reflecting off those glass buildings and it creates heat bubbles inside, right? Proper plans needs to be sanctioned so that we can get rid of those heat bubbles, right? What else can we do? Well, we can, if we find sudden levels of noise or sudden levels of toxicity in certain areas, we can start passing on this information to enforcement agencies, right? There could be a riot breaking out, right? Or there could be a disturbance of peace. There could be a party going out when there are senior citizens in the region, in the vicinity, who might be going to bed, right? So we might be able to use this kind of information to enforce silent zones around hospitals, around schools, around places of where senior citizens live, right? And we might be able to use this kind of time series data to kind of create forecast models about the future as well, right? So this is how sensorification adds on to what we can do with this smart street light, right? What else can we do? Well, if I know about what is the mean time to failure of a particular light, then I can start identifying when these lights will fail, right? Not only can I do that, I can not only predict, I can actually solve a traveling salesman problem and create these optimal routes for the maintenance team so that they are taking out lights which are closer to their mean time to failure, right? I can not only, I'm predicting failure, I'm creating a maintenance schedule well in advance, right? So that I'm not responding to the situation, I'm not in a reactive mode, but I am now going into a predictive mode, right? Data gets fed into a mobile app that is used by the field force, right? So they know exactly which light to fix next, right? And as part of my algorithm, I can factor in the distance, I can factor in the salary of the people who are involved, I can factor in the cost of diesel in going from one side to other, right? So I can have a multi-parameter optimization, right, with respect to identifying these maintenance routes, right? What else can I do, right? Well, what if I can now start putting a camera on top of a smart camera on top of the smart light, right? And I start using it to count things, right? Then there are very many things I can count under a street light. It's high up there, it's 2 to 3, it is at least 3 to 4, 5 meters high. So it has a wide angle of observation, and I can count multiple things. I can count objects, I can count people, I can detect number plates, right? So I can now start looking at deploying several models on top of this street light and use it to look at citizen movement density, right? How many people are actually going underneath that street light, right? At what time of the day are they going underneath the street light? This allows me to create a utilization metric for the street light, because if I have a street light and nobody ever goes underneath that street light, I don't know if that street light is actually serving any purpose, right? So, I can improve the lifetime of my network by replacing the bulb on that particular street lamp with one that is closer to its mean time to failure, right? In that case, what will happen is I will increase the lifetime of the overall longevity of my entire street lighting network, right? So these utilization scoreboards are great, right? I can create this light rotation schedules, like just like you rotate your lights, your tires in a car, right? Just to even out the wear and tear, right? You rotate the front wheels with the back wheels. Right? Similarly, you can rotate the lights around, and the overall network lifetime increases. Right. You can do traffic segmentation and OCR on top of it, right? Remember, I told you that we can use a lot of services already available on the cloud and use them to convert, pictures to numbers, pictures to image, pictures to text, right? That can be used for traffic segregation. What kind of traffic goes underneath that particular street lamp? Is it mostly cars? Is it mostly cycles, right? Because each of them may require a different kind of lighting, right? With vehicular traffic, which are traveling at higher speeds, you may want to have a wider angle of the lighting, right? With pedestrian traffic, right? You want a slightly more focused lighting, right? So that they don't see, they can see the obstructions as they are as people are walking by, right? I can even use these smart street lights now to keep track of public property, right? Keep a track of how many benches are around, how many local gates are around, right? So I can do this object, I can do image classification, I can do object localization, object detection, instance segmentation. All of these aspects can be built into the smart street light, right? By building this, I have now created a new capability, right? Because I understand light, I understand humans, I understand objects. Bringing all of these together allows me to now start creating contexts, right? What are contexts, right? Things like, say, follow me lighting. It is information from one light, from one street light being passed on to the next street light, right? So they kind of act in unison, right? Or it could be context with respect to identifying what kind of people have gotten around, right? Doing clustering of people, and based on that, I can now start to show them ads. I can now start to show personalized ads which have a higher probability of reaching its target audience and help and creating a decision in them, right? This kind of context-aware advertising, pushing ads over a Bluetooth network, right, to passerbys, right? That's another area where I can identify the group of people, whether it is one person walking alone or a group of 3 or group of 5 people, right? These are the kind of clusterings that we can get out of a smart, of a context-aware IoT system, right? Now, of course, there's one thing that I haven't mentioned over here is that transferring data from a video, right, a video feed is going to be expensive, right? So, there is a trade-off that is happening. We started off with just being able to control the lighting, and now we are asking for a high bandwidth pipe. But with smart city networks, with companies like Tata Teleservices or Cisco deploying city-wide Wi-Fi networks or city-wide 5G networks, right? This kind of bandwidth may be possible, right? Because remember, the street light is a powered device. It does not have the same kind of power restrictions as a battery operated device would, right? So it can afford the bandwidth for image and video transfer, right? I can have a CDN service, right? A content distribution network. So if I look at certain set of group of people which fits a particular demography or fits a particular target group, right? Then I can show them specific ads that I'm downloading over the internet, right? So these kind of things can be done, right? For push advertising. What else can I do? Well, my street lamp has a fixed spatiotemporal alignment, which means that it has a location, well known, unambiguous location in space, and it knows the current time, right? So I can now start asking questions of it, right? Remember that the street lamp is public utility, and in a city area, there could be multiple people coming in from different countries, different cities, who may or may not speak the local language, right? So I can have a microphone and a speaker plugged into the street light, connected with an Alexa or a Cortana or a Siri service, and ask it questions like public translation services, right? I can ask it location-aware queries about how far is the nearest hospital, because the street lamp knows its location. So it can give me responses relative to its current location. Or I can ask questions which are temporal in nature, right? When will the next bus be here? Because it requires a spatial dimension as well as a temporal aspect to it, right? And I can use, Amazon has this amazing tool, amazing NLP service called Amazon Comprehend for document NLP, or it has Poly for text to speech conversion, right? We can build voice models based on these, right? I can take this even more further, where I am looking at video streams. I'm looking at gesture and intent recognition by processing, videos as a sequence of frames, right? This allows us to do things like weapon recognition or mob identification, right? It allows us to do things which were not possible before, and this is where gesture and intent recognition comes into the picture, making the street light quite a bit smarter, right? That can lead to an auto alarm, right? I can do context aggregates. Context aggregates are not about just the local context of a particular street light or of a set of street lights, but across all the street lights, the context of all the street lights across the city, right? This gives me the ability to do crime prediction, to do epidemic arrests, right? It allows me to identify hotspots for particular problems across the city. And this is how a street lamp, which was a mere utility and a cost to the government, can become the source of truth for a number of civic services and improve the government to citizen relationship, right? This is how a smart city kind of becomes a light becomes a smart light, growing its IQ by creating new applications, by enabling new features and functionalities, some of which may look like science fiction today. But remember, the concept of smart spaces, the concept of IoT, of ubiquitous computing, is not a story of today. It's a story from 30 years ago, and today we are there. So there's nothing that prevents us from implementing these set of rather hypothetical solutions that I came up with today in the next few years. That's where IoT will take us, right? It's not in that realm of generalized AI. Remember that. Smart systems, smart products does not mean that it solves all of life's problems, right? It is still rule-based event outcomes. It is still complex event-based processing based on known context and on probabilistic searching through solution spaces. It is not able to infer context across disparate data sets or event streams. So we are today somewhere in between. That is what the level of AI is enabling us to do, right? Somewhere in between robotic intelligence and generalized intelligence. So even though in my IQ meter I've gone up to 10, there is still a long way to go to probably catch up with what we consider as human level intelligence, right? With that, I will close my talk. I think we are almost at time, right? And I would be very, very happy to take questions.
Thank you, Mr. Raichaudhuri. If anyone have any question, then please ask to Mr. Raichaudhuri.